Dear colleagues, once again, good afternoon. We're very happy to welcome you here at Россия Сегодня news agency, our multimedia news center. I would like to welcome all the journalists and students, and I'd like to welcome also everyone who are watching us online. Our topic is new materials, the living biological world as the source of inspiration. This is part of the Sputnik Readings project, and our guest today is a professor in material science and metallurgy at Cambridge University and a member of Mrs. Advisory Council, Lindsay Greer. A round of applause for the professor. Lindsay, you have the floor.
Much. Can I first check that the technology is working okay in terms of sound? And you can hear me, and the translator can hear me. Good. So my topic is making materials. Of course, mankind makes many kinds of materials, steel and so on. But can we draw some inspirations from what I've called the living world? And I will explain what I mean by that. Our topic could be called biomaterials. But in English, the word biomaterial has two meanings. One meaning is materials that the medical profession might use to put into the body, artificial hip joints, etc. So the biomedical materials. That is not my meaning for this talk. Instead, my meaning will be the materials out of which living systems themselves are composed, the materials of which we are made, if you like. Now, we know that natural systems have evolved. There is a process of selection of the fittest for organisms. So if things are to get better, it must mean that the materials in them are also getting better. Those materials should be well adapted for their function. And therefore, those materials should have some interest for us. In fact, they did have interest for our very early ancestors living in caves with no access to steelworks or anything else. They had to make do with the natural materials around them. And some of the very best natural materials came from living systems, leather, bone. These things could provide very effective, strong properties which could be exploited. As we have progressed, we have tended to move away from those natural materials. You see more man-made materials like steel. But maybe now we're rather moving back to those earlier materials to draw some inspiration from what they had to offer. So we'll see what we can do in this regard. And we're going to start with a tree. And our problem for you is to think about the tree not as a biological structure, but just as an engineering structure. So imagine you are an engineer and you are given the job of selecting the best structural material from which to make the tree. You know roughly what you have to do. The tree has to stand up. It must be reasonably stiff to resist moving in the wind. How to choose the best material? Well, we need some way of measuring the properties of a material. Let us imagine a very simple component, a cylindrical rod. It has some length L. We put some load or force on it to make it longer, and we measure how much it gets longer by this extension delta L. You already, of course, know the next point in my argument, which is that F and delta L have a linear relationship with each other. And you can look at the gradient of that line, and that's a property which we could call the stiffness. But that is not very good for telling us the properties of the material out of which this rod is made, because unfortunately that stiffness depends on the dimensions of the rod itself. If I made the rod twice the diameter, it would be much more stiff. And we don't want to measure that. We want to measure something that depends on the material, not the size and shape of this object. We note that this is reversible. That's good. We'll be exploiting that elastic property. And here's the point I've been making, that reversible or not, the property we've got is dependent on the size. How to get away from that? Well, it is to change these properties. So instead of looking just at the load, you divide it by the area to get a property called stress. And instead of extension, you divide the extension by the original length to get a property called strain. And now we plot those against each other. It's really the same plot as before. We again have a straight line showing that reversible behavior. But now the gradient of that line is a property called the modulus, the Young's modulus E. And that is a property of the material, not of the particular component. So that property E is something we can use to tell us whether a material is better or worse for some function. It's a material property. So back to our tree. A branch on a tree has the function of holding the leaves out in the sunshine. It must not bend too much under its own weight. It must not bend too much in the wind. So it must be stiff. It must have a high Young's modulus. And of course, it must not be too heavy to bend in its own weight. So it should have a low density weight per unit volume. We can analyze this amount of bending that it would undergo. We need not worry too much about all the mathematics. The point is to say that if you have a beam, as in this yellow object here, with a force on the end, as a result of that force, the beam shows a deflection, which is this quantity I have called delta. And we can look at what determines the magnitude of the delta. It's this expression. These are various parameters of our beam. We'll focus just on delta itself and on this combination of parameters at the end, which is the density of the material, rho, and the Young's modulus E. In this particular ratio, the square of the density over the modulus. So, in building our tree, we wish to have this deflection be as small as possible. So delta must be small, which means this combination of parameters must be small. Turning it the other way around, this must be as large as possible. And you could express it this way or this way. So we know what we need to do. Now let's compare different materials. We need to maximize this ratio of two parameters. Well, here's a chart of materials properties for different materials. Along the bottom, we have the density, which we already mentioned. So this is a logarithmic scale, a factor of 10, a further 10. Vertically, we have the modulus, factor of 10, factor of 10. In rough terms, we know what we want for our tree. We want the Young's modulus to be large, so we want to be as high in this chart as possible. We want the density to be low, so we want to be as far left as possible. But how exactly to do it? Here's what we want. This line is interesting. If we go from this end to this end, our density goes up by a factor of 10, and our modulus goes up by a factor of 100. So in terms of this ratio, E has increased by a factor of 100. The square root is obviously increased by a factor of 10. The density is increased by a factor of 10. So this is constant. So this is a line of constant value of this. And that line is, of all the positions on the diagram, it is as much towards the bottom and to the right as possible. And that's the worst place to be. So the material which it indicates should be the worst possible material to make a tree out of. And that material is, in fact, soft rubber. It's the material of a rubber band that you might use. And you can understand that making a tree structurally out of rubber band material would not be very successful. Here's another very bad material, the metal lead. Rather soft, rather heavy, not a good material to make a tree out of. As it happens, steel would be quite a good structural material for a tree. Of course, you know that aeroplanes are not made out of steel, they're mostly aluminium. Aluminium is a little bit better than steel. That red line is a little bit further towards the top left where we want to be. But interestingly, of all known engineering materials, the best one is indicated by that line, and I have to tell you that is wood. It's in fact balsa wood here. So it means that if you ignored all the biological functions of the tree, you ask the question simply, what is the best structural material to build a tree? The answer is wood. So it says that nature got there already And it's one example of evolutionary selection giving us something that's well adapted for its function. Wood is the best material to use. Well, this idea of evolutionary selection was, of course, made famous by Charles Darwin, who's one of the alumni of my university. It can obviously have strong effects in other systems as well. But let's look a little bit at wood. It consists of cells. They are cylinders. You might regard them as rather like my pen, but rather longer in relation to the diameter. And most of them are aligned with the axis of the tree, up and down. But imagine that the tree was composed only of cells like this, which are parallel to each other, with nothing linking the cells. The tree would in fact be very weak. You could bend it easily and the cells would bend out of shape. So you must hold it together. So if this is the main axis of the tree, the radial directions have a set of cells holding the main ones together. And that is these ones. Here is a cross-section of the tree. The vertical cells are very obvious, and the radial cells are the ones holding things together. Interestingly, if you imagine looking at this tree, you just look at the surface, there are no cells parallel to the surface. The ones vertical are there, but not the other ones. So to split wood that way is extremely easy. It's very weak in that direction. This is common wood, Scots pine. These are the cells parallel to the axis. These little things look like peas, but they're actually the ends of the radial cells coming out, holding everything together. It's a wonderful engineering structure. This is another cross-section. You know that if you cut a tree across the axis, you see growth rings. This dark band is one growth ring. So as we move up the screen, we're moving into winter. Growth stops on the dark line, and then in the spring, the growth resumes with those fresh cells. This is one of the hardest woods known. Greenheart is the name in English. This wood is exceedingly strong. This material is essentially got no further volume in it. It's completely dense. In fact, the overall density of the wood exceeds 1. So this wood will not float in water. It will sink. Interestingly, it's in the same classification of hardwood that you find the very light material balsa, which is about, well, it's more than 80% air in its dry condition. But it's a wonderful example of a light, stiff material from which we could draw many structural lessons for man-made materials. So back to our idea of people living in caves, maybe 50,000 or more years ago. Here's a chart again of properties. This is density, factors of 10, strength, factors of 10. But the real point of this chart is to show you the range of available materials. And I mentioned to you that some of the most interesting materials were natural materials. So we find here wood, shells, antlers of animals, very impressive properties. We have, of course, moved out of caves. So if you were living at the high point of the Roman Empire, this would be the range of materials available to you. 1900, that would be the range of materials available to you. And today, this is the range of materials available to you. What's interesting is that this great expansion in range is largely in the direction covered by wood. It takes its inspiration from the cellular structures of wood and manages to take them even further. So you can develop metal cellular systems. The cells could be so-called closed, so these are bubbles inside the system, making it low density. Or those bubbles could link with each other, giving you a so-called open cell foam. You could imagine that a liquid could travel through that, so you could use this material as a filter. These are examples of components made from foamed aluminium. They're light, stiff. Here are filters from nickel. Another point to make about these materials is not just that they provide inspiration in terms of properties like strength and density, but in other ways also. The tree only ever exists in the natural temperature that it finds at the surface of the Earth. It doesn't have any high temperature processing at 2000 Celsius or something. So the energy input to make a tree is minimal compared to the energy input to make a man-made material. And this is a chart of one property, namely the stiffness, the Young's modulus of a material, as a function of energy input. And for energy input, you could think of how much oil you have to burn to make the material, or you could think of how much CO2 is put into the atmosphere. In any case, high energy is a bad thing, and low energy is a good thing. And these natural materials, particularly the woods, can deliver very high performance in terms of properties with exceedingly low energy. And that's characteristic of the natural materials. There'll be very low energy input as well. So you get performance with low environmental impact. We'll now turn to a completely different world, if you like, namely the view of the spider, which would like to attract some food in the form of flies. Of course, when the fly comes into the spider's web, from the spider's point of view, it would be a disaster if the web was to break. The web must be strong enough to receive the impact of the fly, so it must be good at absorbing energy. So we can come back to our chart where we looked at Young's modulus, where we had stress and strain, and there's this linear reversible relationship. The gradient is the modulus, and the modulus is a property of the material. If you stretch the fiber, you put in energy, you do work, you can let it go back to its original length, the work comes back. The amount of energy is the area under the curve. It's this triangle, this pale blue triangle. And quantitatively, that area is given by this expression. It's the square of the stress you reach divided by twice the modulus. So we know what we have to do if we want, like the spider, to maximize that energy. The first thing is you want to make the fibers stronger so you can stretch them further. So we increase the stress. That obviously increases the area of the triangle and the energy. The Young's modulus is more difficult. I think if I approached you with a question about a spring and I asked you if the spring is to store more energy, should you choose a material with a high modulus or a low modulus? Well, the natural answer would be to say high modulus. But actually, what you want is to do the opposite. You want to decrease the modulus, because by lowering the gradient, you of course get a greatly enlarged area, which is the energy. So we know what we want from the point of view of the spider. Does the spider actually pay attention to this? Well, yes, it does. When the spider makes a web, it has two types of thread in the web. The ones that are radial are those straight lines you see top right. They need to be stiff because you want to hold the web in place. And then the other ones, which form a sort of spiral from the center, are the so-called capture threads. Those are the ones that are going to be used to catch the fly. You don't want those to be stiff. You want those to absorb lots of energy, so you want a low modulus. And with exactly the same chemistry of all of these threads, the same chemical composition, the spider manages to make threads for the frame that has a modulus of 10 gigapascals, and for the capture lines, a modulus of 0.1 gigapascals. In other words, a factor of 100 different in the modulus is engineered by the spider for this purpose. It achieves that by allowing the polymers here, the long chains, to be more or less independent of each other, whereas here they're linked into crystalline structures bound locally to make the overall material stiffer. So here's the web. These are the stiff lines of high modulus, 10 gigapascals, and these are the capture lines of low modulus at 0.1 gigapascals. In fact, if you look at those capture lines up at the top, you'll see that they are not straight. They're hanging under their own weight, so low is the modulus. They're stretching under their own weight. So, of course, we need to look at one of these charts. We know what we want to store energy. We want a high strength. And we now know that we want a low modulus. So we want, on this chart, to be as far as possible towards the bottom right. Well, here's a map of all the materials that nature has available. Here's the relevant line of the gradient we have. And by now, you will, of course, not be surprised to find that of all the available materials, nature has chosen the best one. This is, in fact, the silk from a spider's web capture line, which has the best combination of properties of any of the natural materials. It's significantly better than anything else. We've talked about absorbing energy, but of course the fly does not wish to provide a sporting or entertainment opportunity for the fly. From the spider's point of view, it would be bad if the fly comes in and then bounces right out of the web like a trampoline. So in fact, it's quite important that the web absorbs the energy and does not return the energy. Well, the spider has sorted out that problem as well. So your normal elastic curve is linear and completely reversible. This is not. This is the curve for such a web material. So on loading, you follow this curve. Remember, the energy is the area underneath. So there's a big area. What on unloading, it follows this curve. The area underneath is much smaller. In fact, it's only 35% or so. So it means, yes, the web does return elastically, but it only gives back about 1/3 of the energy. 2/3 has been absorbed. It achieves that by changing the structure as we go round this loop. We do go back to the starting condition, but it changes its structure to avoid this problem of acting as a trampoline. And the structure changes between two forms called beta sheet and alpha helix. We need not worry about the detail, except you can see already those two structures look rather different, which says actually it's not so easy to change from one to the other, which is exactly why the curve of the elastic properties has the sort of behavior that it does. The modulus is controlled by the amount of cross-linking, and that's important in governing the different types of thread in the spider's web. Let me just stay with the comment on spiders' webs for the moment. If they're extremely good at absorbing energy, you could think of a completely different area of application. Think perhaps of an aircraft carrier, and planes have to land on the carrier, and you need a so-called Arrestor cable to stop the plane. The function of that cable is to absorb the energy of the landing plane. So we can ask the question, would the material of spider's web be a good material for these Arrestor cables? The answer is yes, it would be rather good. But unfortunately, it would be too good, because it absorbs the energy, and of course that energy must go somewhere. It is dissipated as heat. So the Arrestor cable made of spider's web would heat up so much, it would burn itself. It would last only once. It would go into flames or something. It would be destroyed by the amount of energy it itself would absorb. Our last topic takes us again to a different world. Namely the world of the frog. This particular frog, if you like, carries a Canadian passport. It lives in Canada and is possibly the cleverest frog in the world. It solved a difficult problem, this frog. Living tissues, plants or animals, do not survive freezing. And the reason is rather simple. You have the living system composed of cells. Here is a schematic of a cell. The cell, of course, is a bag of water with a membrane around it. Of course, inside it is not pure water, it's a salt solution. Imagine that you start to grow some ice inside the cell. Here's the ice crystal. The ice crystal, unlike the liquid, is essentially pure H2O. So the salts in the liquid are now more concentrated than before. Previously, the liquid inside the cell was in balance with the liquid outside in terms of salt concentration, so-called osmotic balance. But if we now make this salt concentration higher, then the osmotic balance is destroyed. The cell will absorb water from the outside by osmosis through the membrane. Of course, drawing in water from the outside simply allows the ice to grow even bigger, which draws in even more water. So the cell will just keep getting bigger and bigger and bigger and will eventually rupture the membrane. It will burst, and then the cell is dead. You've destroyed the biological structures. And for our friend, the frog, this is a difficult problem, because the frog made a very bad life choice. It decided to live north of the Arctic Circle. So in the winter, this frog has no choice. It will freeze. In fact, it freezes completely solid. It cannot avoid the formation of ice. And yet, in the spring, the frog thaws out, the ice becomes water, and the frog hops back to life. This is exceedingly unusual for any living system, even an individual cell. So understandably, many biologists and medical people have been fascinated about how can it be possible for this frog to achieve this. And it does it very simply and cleverly by admitting that it is going to form ice, whether it likes it or not. So its only question is where to form the ice. We've already seen that forming the ice inside the cell is fatal. It will kill the cell. So the option is to make sure that you have templates to nucleate the ice only outside the cell. Now all those processes I talked about before operate the other way around. Now the osmotic balance is disturbed, but it's now the fluid outside the cell that becomes more concentrated in salts. That draws water out of the cell, so the cell becomes dry gradually. So your mental picture of this cell, of course, the actual cell is rather small, but you should picture a grape. And you make the grape more dry. It shrinks and forms a raisin and gradually becomes hard. So what was liquid, more or less, inside the grape becomes a solid. It actually is a solid glass. It's not crystalline. The viscosity gradually increases and you form a glass. In the actual cell of the frog, the water doesn't just have salts in it, it has quite high molecular weight sugars. And it's rather similar to the consistency of this raisin that it would form when it shrinks on drying. Of course, come the spring, this ice turns back to water, the cell absorbs that water, and what doesn't happen easily with a raisin, but your raisin goes back to being a grape again. You rehydrate the system. You have not destroyed any of the biological structures, and so the cell, in effect, comes back to life. We normally think of making a glass by starting with a liquid and cooling it. If there are any metallurgists in the audience, there might be one or two, they will recognize a phase diagram. Of course, in the diagrams that metals people normally meet, this would be one metal and another metal mixing with each other. In this case, the two things mixing are water and a sugar. In this case, the particular sugar is sucrose, but in fact it doesn't matter. It could be any type of sugar, really. The vertical axis is temperature. So on the left-hand side, we have pure H2O, which at high enough temperature, of course, is water. We cool and it freezes to ice. Well, water cooled, forming ice, that turns out to be easy. On the other side of the diagram, it would be pure sugar, which at high temperature is liquid sugar, and at low temperature should be crystalline sugar. But that crystallization is rather difficult. In fact, it rarely happens naturally. The case of interest for the frog is in the middle, because it has a cell solution that, of course, is mostly water, but has dissolved sugars. If you were to cool it, it will harden eventually into a glass. But that's not the only way the frog can achieve it. It can achieve it by changing its composition. You take water out, you make the system dry. So on this diagram, that means moving to the right. And you cross this so-called glass transition line by a different mechanism, not by changing the temperature, but by changing the degree of hydration. You take water out, you form the glass. Here is an example of a glass. You have a solid structure, but it in some way preserves the arrangement of the liquid. It's formed by gradually becoming more viscous, and definitely not by freezing and forming a distinct crystal structure. If you did form crystals, the cell would be dead. And in the winter, this frog is 100% solid. It's about 50% ice in this tissue outside the cells, and about 50% of this sugar-based glass. Nothing is happening in the frog. It's dormant. But when you put water back in and it thaws out, it comes back to life. So it's clearly of immense interest in medical science, whether it be preserving organs or something else. Please do not try any experiments with frogs when you get back home. Firstly, you will have the wrong type of frog, which doesn't have its Canadian passport. And secondly, don't try liquid nitrogen, because it's very important that the freezing is slow, because it was to do with osmosis of water through the cell membrane. That takes time. If you were to plunge this frog into liquid nitrogen, I can assure you the frog would not survive. So that brings us to the end of our presentation, to say that we've seen an example of a plant tissue, wood, which actually has extremely impressive mechanical properties. So much so that we can regard wood as an extremely important engineering material in its own right. And indeed, of course, it is the major construction material after steel and concrete. It's also a high-tech construction material. And then we've seen examples of the exploitation of elasticity, in this case, to provide a nice food source for the spider, but it involves quite a lot of materials engineering, which we could imagine exploiting in various ways. And the frog takes us from the area of purely structural materials into the area of biomedicine, to say that the way materials change their structure between liquid, crystal, or glass is something that can be exploited in various ways. In this case, for the frog, it's exploited for the rather serious business of survival. So it's obvious why Darwin's selection has come up with an answer to this problem. If it hadn't, we wouldn't have the frog at all. And we can draw other medical lessons from that. So I will close the talk at that point. Thank you.
Thanks, Professor. Now we are moving into the Q&A mode. Please use the microphone. If you have any questions, please let us know. Okay, go ahead. I would like to thank you, first of all, for this very interesting lecture. Could you please give me the phase diagrams with water and sugar? Could you please go back to the slide with water? Could you please go back to the slide with water and sugar? No?
I take my...
Maybe I should have this one.
Just a second.
Yep.
Okay.
Here we go.
Okay.
So, could you please go back to... could you please go back to the slide with water and sugar phase diagram? And first of all, of course, thanks for your great lecture. So, on the x-axis, you have the content of sugar in water. Is that right? So on the left it is 0%, which means that it's pure water. And on the right, it's pure sugar. So, my question is this. Where you've got pure water, this is a solid water at the minus temperature. But there's the line at minus 120 degrees. What does it mean? Is there any other phase transition between solid and what in water? Did you understand the question?
And I did understand the question. You are quite correct that this appears to indicate...
Professor, could you pick up the microphone, please?
This appears to indicate two transitions. The point is that you normally imagine when you cool the water, you form ice, right? And that is what would happen at 0. Imagine you did not form ice, because ice needs a particular nucleation event to trigger it. So imagine that did not happen. Then you would continue to cool the water. So in fact, what you would have here would not be ice, it would be water, so-called supercooled water. It's not the equilibrium state of the water, it has a much higher energy in fact. So the water here is, if you like, very unhappy. It wishes to be ice, but it has not managed to become ice. Then if you cool, even without formation of ice, the water will become solid. But it will become solid that preserves the structure of the liquid and is no longer a crystal structure. That is the so-called glass transition. Now, it so happens that in this diagram, we have data points for where the transition occurs. And you can see that at this level of sugar, it would occur here, 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 here. There are no data here. This is, in a way, a hypothetical line suggesting where the glass transition should occur if it was found in pure water. But you are exceedingly unlikely to be able to find it in pure water. Does that answer the question? Yeah. Okay.
My question is about the frog. You have said that this is a unique solution, and that means that other animals don't have sugars in their cells, right? So, are there any advantages? Are there any other advantages that this frog gets from having sugar in her cells?
The question. It's not a unique solution. We all have sugars in our cells. It only depends how much. I have been emphasizing in this talk that one of the main difficulties for life is how to survive freezing. And that is the principal question of interest for the frog. But I said that the mechanism of the frog adopted involves dehydration of the cells. We can then think in parallel to that the other threat to life on Earth is not freezing, but in fact dehydration itself. Imagine you have a desert. You have some plants. Occasionally there is some rain with some water. But the plants must survive long periods without water. One of the mechanisms they choose is exactly the same mechanism as used by the frog. Namely, they have high molecular weight sugars in their cells, so when they dry out, they form a glass and do not form crystals. Interestingly, exactly this same defense mechanism against death by dehydration is built into us. So if you start to dehydrate humans, we start converting starches into high molecular weight sugars in our own cells, which is exactly what we would need to do if we wanted to survive dehydration. Unfortunately, humans are not very good at it. Or put another way, it would be messy because, like the story I told of the grape becoming the raisin, the cell survives, but obviously the volume changes. So if we were to survive dehydration, we would shrink and we would become very little people. But unfortunately, our bones don't shrink, so we would be a very messy operation. But if you were able to debone us, so you take all the bones out, probably we could survive dehydration with suitable treatments. To give you a more serious answer to your question, the point is that this business of sugars in cells is universal, but the mechanism is taken to an extreme in the frog. But in fact, sugars exist in many cells, not just in the frog, also in small insects, where they're used for exactly the same purpose, and in many, many plants.
I would like to thank you for the lecture. I've got one question. Is it possible to create such biomaterials using modern technologies, and does it make sense to create such materials like spider silk, for example?
It's a very interesting question because of the very particular example of spider silk. Because you could imagine that you would rather make the silk that silkworms make to make the cloths, to have an artificial silk. And of course, this has been tried from very early days, and we are still very, very bad at it. The spider is so far, or the silkworm, all of these animals are rather better at making these fibers than we are. But we have a rather clear idea in that case of what we are trying to do. We're trying to manipulate the chemistry and the flow of the liquid to get essentially polymeric molecules correctly designed and aligned. To broaden your question away from fibers, there of course is interest in making materials that draw their inspiration from nature. One example would be the armor for tanks, for the army, where they must be very resistant for shells coming in to hit the armor. And one technology to do that is to make the armor consist of layers, which in a way is drawing lessons from seashells. For example, mollusk shells can combine layers of rather brittle ceramic with polymeric layers and still achieve out of those uninteresting materials a rather interesting composite material with extreme high toughness. The other thing you could think about is that we know that woods can be rather successful materials. Perhaps we could breed new types of tree to make better woods, or in the modern era we might think of genetic engineering of different tree species, particularly something like fast-growing bamboo, which is an excellent, efficient, environmentally friendly way of making high-performance fibers to incorporate into a man-made material. You could go even further. You could think of genetically engineering bacteria to grow particular molecules which you deploy as catalysts, battery electrodes, etc. And there are people working exactly on this. It should not come as a surprise because, after all, we use this biology approach for all sorts of materials. We happen to call those materials food. We use natural agriculture to grow our food, whether it be meat or vegetables. Why not equally do it to grow structural materials or functional materials for semiconducting light displays or whatever? In principle, one could conceive of doing that, and that's probably defining a whole load of directions for the future.
Hello. Thank you very much for your lecture again. And the question is, do you think in the future these technologies that you are talking about will be better spread than the already technologies like metal technologies that we have right now? Do you think that in the future those kind of things will we use more than industrial things?
Well, I think that everything will evolve rather slowly. You shouldn't imagine an overnight revolution in the materials that we use. The existing materials are used for quite good reasons, and even if you come up with a new material which is better, it's a high risk for industry to change to a new material if they already have a material which works well. So we won't see any overnight changes. But we all know within our own lifetimes, we've seen a lot of more use for polymeric materials and less for metallic. Those sorts of trends we will certainly see continuing. And I think we will see quite a lot of application of biological methods for growing functional materials. When I mentioned battery electrodes a minute ago, I had a particular example in mind of a professor at MIT who's doing exactly that, using genetically modified bacteria to grow material relevant for battery technology. It won't necessarily be labeled as such, but it's a way of making the material.
I would like to thank you for your lecture too. It was very interesting indeed and quite inspiring. But when you were speaking about the spider silk, you have highlighted one of the possible drawbacks of this material. You said that when you used your example of Arrestor, that if it were used as the Arrestor, it would absorb too much energy and will just burn and decompose. And I think that this is quite common property for all the other of the examples of materials from the living world, because they are organics or are made of carbon. Yes. What do you think are the possibilities of creating inorganic and non-carbon materials which would recreate their similar structures in the future?
Well, it's a very good question. I emphasized the point about the biological materials being environmentally friendly because they were made under ambient conditions without high temperatures. But you have highlighted the other aspect of that, which is, of course, the biological materials are exactly designed for operation at ambient temperature. They are not designed for operation at 1,000 Celsius or whatever. So we do need to think of going beyond just the range of materials we have. We could highlight that nature gives us several examples of very excellent control of inorganic structures, as in seashells. So you take a shell of various types of mollusk. It is composed of calcium carbonate. But calcium carbonate has many crystal structures, notably calcite and aragonite. The biological system manages to choose which crystal structure to form from identical chemistry. They're all CaCO3, so aragonite or calcite. Furthermore, it manages to control the crystallographic orientation of these phases. Furthermore, it manages to package them in thin controlled layers with polymer sheets between. And as a result of that, the hard material of the shell, the calcium carbonate, as chalk for writing on a blackboard, has a certain toughness. As the shell on the animal, it has a certain toughness. The toughness on the animal is 3,000 times the toughness of the native chalk as a result of this structuring. So that sort of capability for patterning an inorganic material, there's really no reason why that should be limited to calcium carbonate. Why not use other compounds? And that might be a matter of adapting existing living systems. For example, our bones are a calcium phosphate, but are also very well engineered. There are other inorganic minerals used already in living systems, but the really exciting bit, of course, would be to engineer your systems to deal with completely different inorganics. I mean, why not have your creature grow you a gallium arsenide crystal of the right size to be a quantum dot? One could imagine that in principle that would be possible. Yeah.
Еще один вопрос о паутине.
I have another question about how to generate those materials. Why doesn't a spider, unlike the fly, gets caught in its own web?
The spider, of course, knows the web it's using because it made it, and it walks out along the frame lines, which are nice and stiff. And you'll have noticed that the capture lines not only are so soft that they hang under their own weight, their weight is increased by having little beads of glue on them. So the spider doesn't take any risks. Not only when the fly comes in is there all the mechanism for absorbing elastic energy, but there are also these sticky patches so the fly will stick. The further aspect of operation of the spider's web is interesting. The capture lines have such a low modulus and such a high strength that you could take a length of the capture line and pull it to 3 times its original length, and it would not break. So what happens is the fly comes in, the capture line becomes much longer. The fly immediately knows it's in trouble and starts to think about getting out of there in a hurry, which just means that it tangles up in this extra length of line. The spider has all the time in the world to wait for the fly to be tangled up and then carefully walk out along the nice stiff frame lines that have no glue on them. So it's an unequal competition.
Well, if there are no more questions, let's wrap up this lecture and let us thank our lecturer for carving out time from his very, very busy schedule and joining us here. Thank you very much, and we thank everyone who has joined us here and online. Take care and goodbye.